Good morning, everyone. Presenter is Brij Tewari from University of Guyana. Topic of my presentation is metal complexes in biology and medicine, the system, aluminum third, chromium third, iron third, norvaline. Abstract. In coordination compound studies, knowledge of stability constant of complexes is necessary. The preliminary quantitative treatment metal complexes can offer their actions such as anti-inflammatory, antimicrobial, antibiotic, and antithyroid and anti-cancer compounds. Metal-based drug bioactivity can be increased by metal chelation, which in turn increase their absorbance and stability. Recent advances in inorganic chemistry have made possible formation of number of transmetal complexes with organic ligand of interest which can use as therapeutic agents. Aluminum prefer oxygen donor groups for complexation. The stability of complexes in biological system depend on pH, which in blood plasma is 7.4. Chromium is a very adaptive metal and it can form copious species with variable oxidation numbers from -6 to +6. Iron is a component of heme and chlorophyll and serve as micronutrient of plant and animals. Ferric ions from industrial effluent has potential to poison animals and plants. Present technique involving the use of paper ionophores is described for the study of equilibrium and boundary complex system in solution. The method is based on movement of spot of metal ion in an electric field at various speeds of background electrolyte. A graph of pH versus mobility was used to obtain information in the boundary complexes and to calculate its stability constant. Using this method, the stability constant of boundary complexes metal third norvaline has been determined to be 8.73 plus minus 0.03, 7.20 plus minus 0.04, 9.00 plus minus 0.01, 7.41 plus minus 0.07, and 9.43 plus minus 0.01, 7.66 plus minus 0.11 logarithmic stability constant values respectively. At a ionic strength of 0.1 mole per liter and temperature of 35 degrees centigrade. The first and second stability constant value of metal complexes forward order iron is greater than chromium than aluminum. Introduction. Iron is a metal without which life cannot sustain. Aluminum is an indifferent metal, toxic at high level. Chromium is essential beneficial metal which is helpful for healthy life. Aluminum, chromium, and iron element in human diet milligram per day at normal and toxic level are 2 to 15, 5000, 0.01 to 1.2, 200, and 6 to 10, 200 respectively. Mujika et al. Reference number 2 has described a detailed account of interaction of aluminum with protic side chains and how aluminum can exert oxidative stress by stabilizing superoxide radicals either as mononuclear aluminum or clustered in biomite, reference number 2. The Howe et al. Reference number 3 posted several examples where aluminum has been shown to irreversibly perturb and or stabilize the natural conformation of molecules known to be important in energy metabolism, gene expression, and pathological signaling in neurological disease. Megenser and Gibbons, reference number 4, has described a complex world of chromium species and their activity with DNA and other biologically relevant molecules in vitro to inform a more complex understanding of chromium-6 mediated toxicity. Levick et al. Reference number 5 has aimed to present current knowledge about chromium, its organism, and possible mechanism of action also in metabolic disorders such as diabetes or obesity. Karajewski et al. Reference number 6 has determined how a high-fat diet supplemental with various forms of chromium affect hematological and immune parameters of blood of rat. A review of chromium uptake, translocation, and accumulation in plant discussed by Abdullah et al. Reference number 7. It also provides a model to unravel the complexity of chromium plant interaction utilizing system biology and integrated omics approach. Rolish et al. Difference number 8 has presented a view on iron metabolism and discussed role of calcium, magnesium, and trace elements, copper, zinc, lead, mercury, nickel, etc. in absorption and transport of iron. A review on the physiological significance of iron homeostasis in the body, the, the potential contribution of ferroptosis to the etiology and development of human disease, along with evidences supporting ferroptosis as a therapeutic approach, has been described by Ru et al. Kula et al. Difference number 10 has reported a review to systematize the available data on role of iron in the function of nervous system, especially in the brain. Contour Giri, reference number 11, has discussed iron load toxicity in medicine from molecule and cellular aspect to the clinical implications. Synthetic method, and pharmacological potential of iron immune complexes having in vitro activity to significant clinical performance from 2016 to present has been described by An et al. Difference number 12. Aluminum third, chromium third, or iron thirds are well known for its biomedical application and toxicity. Difference number 13 and 14. Norvaline is an amino acid isomeric with valine and usually made synthetically. Norvaline may have been more abundant protein components during early stage of cell evolution. It has several significant applications in biological systems. ESO has done comprehensive study on paper aneuphotic migration of metal complexes. Paper aneuphotic technique usually suffer from several defects: electroosmosis, temperature during electrophoresis, capillary flow on paper, adsorption affect the mobility of large molecules. The present technique is free from all these irritating factors and very conveniently used. It gives result in fair agreement with accepted literature values. The procedure electrophotic technique is used to study the mobility of metal cation spot on paper strip soaked with background electrolyte at different pieces and determine stability constant of complexes formed between metal cation and anionic ligands. Present work described a paper electrophotic method for determination of stability constant of aluminum third, chromium third, and iron third, norvaline bonding complexes, and their possible medical applications. Experimental. Now, instrument is Systonics Neroda India Model 604 electrophotic equipment, horizontal cum vertical type model 604 has been used. Two hollow rectangular plates covered with thin polythene sheets have been used through which thermostated water circulating for controlling the temperature. The tanks were closed with transparent PVC molded lid. The whole assembly is tight, which prevents moisture generate that may upset the equilibria in a paper strip. This design is thus keep to minimum the disturbing effect of evaporation from unwanted liquid flow in the paper. Each electrolyte tank contains a separate electrode chamber. Wattman number 1 filter paper for chromatography was used for the purpose of electrophoresis. IDCO Hyderabad India model EL1 to 10 piece meter using a glass and aluminum electrode assembly working on 220 volt 50 Hz stable state main was used for pH measurements. pH meter was calibrated with buffer solution of pH 7.0. Paper electrophoresis equipment model 604. Now, this figure shows the paper electrophoresis equipment model 604. This one 604 and electrophoresis assembly covered by thin polythene sheet. This figure number 2 shows the water supply. This is 3. Figure number 3 shows the water supply in upper and lower metallic plates. Figure 2, this is paper electrophoresis. I placed the 2 before this. 2 paper electrophoresis equipment model 604 and water supply in the lower metallic plates. And this also shows the paper is placed on the lower metallic. Now, this figure 5 shows the scheme for paper electrophoresis setup. First step will be the main power supply, then electrophoresis supply 604, then paper strips were covered, spotted with metal ion solution and mounted on the insulated metallic plate. Next step, both electrolyte wedges were filled with 150 ml of background electrolyte. Next step, second insulated plate was placed on the moistured paper strips. Next step, in order to keep the temperature constant, thermostated water 35 degrees centigrade was circulated into the both insulated plates. Left the equipment for 10 minutes to ensure the weighting of the paper strips. A 200 volt potential was applied between the electrophoresis carried out for 60 minutes. If we apply the 220 volt, then 1 hour. If I applied 110 volt, 120 minutes. Paper strips were removed after electrophoresis by glass rod and dried metal spots were detected by specific reagent. Corrected movement of metal spots were measured and mobility was calculated. Next step. Preparation of metal solution. Aluminum, trivalent, aluminum, chromium, and iron percolate solutions were prepared by preliminary precipitation of metal carbonate from 0.1 molar per liter solution of aluminum, chromium, and iron third sulfate with the solution of sodium carbonate. The precipitate were washed with boiling water and treated with measured amount of 1% perchloric acid. These were heated and filtered. Metal content of filtrate were determined and fine consistency kept at 0.005 mole per liter. Now the sodium hydroxide solution. Carbon dioxide free sodium hydroxide solution was prepared by dissolving 500 gram of sodium hydroxide in 500 milliliter of water in the flask. Flask was left overnight. Liquid was filtered rapidly using high vacuum pump. A suitable volume of filtrate was diluted and concentration determined by filtrate against the standard oxalic acid solution. The solution 2 molar was obtained by suitable dilution. The concentration of starch solution was checked time to time. Now, detecting reagent. Metal spots were detected on paper using aluminum solution for aluminum third, 0.5% solution for of potassium ferrocyanide for iron third, 0.1% solution for of PAN for the chromium third, 0.005 mole glucose solutions are prepared in water and used as electroosmotic indicator for the correction due to electroosmosis. A saturated aqueous solution of silver nitrate was diluted with acetone 20 milliliter. Glucose was detected by splitting with this silver nitrate solution and then 2% ethanolic solution of sodium hydroxide until black spot is formed. Background electrolyte. Background electrolyte used in study of binding complexes were 0.1 molar perchloric acid, 0.01 molar norvaline. The system was maintained at various pHs by addition of sodium hydroxide. Stark solution of 5 molar perchloric acid, 2 molar sodium hydroxide, 0.5 molar norvaline were prepared. Each solution was standardized using appropriate procedure. For recording the observation of particular metal ions, 2 strips were spotted with metal ion solution along with additional 2 spotted with glucose using 1.0 microliter pipette and mounted on insulated plate. Each of the 2 electrolyte wedges were filled with 150 milliliter of background electrolyte containing 0.1 molar perchloric acid and 0.01 molar norvaline. The paper became moistened with background electrolyte solution due to diffusion. Second insulated plate was placed on paper strip, then thermostated water 35 degrees centigrade was circulated plate to keep the temperature constant. A direct 200 volt potential was applied between the electrophoresis carried out for 60 minutes. After which these strips were removed from the tank and dried. Metal ions and glucose spots were detected by the specific reagent. Electrophoretic observations on metal ions were recorded at various value of background electrolyte. After applying the correction factor, the observed mobility is given as U equal to D plus minus dg upon F. where D is the movement of glucose, overall mobility, U is overall mobility, D is the movement of glucose spot, movement of the spot, metal ion spot, D is the movement of glucose spot, X is the potential gradient, and T is the time of electrophoresis. In this case, time is 1 hour and X is the potential gradient which is calculated by applied voltage upon length of the paper strips. The speed of metal complex ions are reported with pH values. A plot of pH against pH curve for metal third, this is third, not the second. Norvaline is shown in figure 5. Now the result. The plot of overall electrophotic mobility of metal spot against pH is shown in figure 5. A constant speed over a range of pH is possible only when particular complex species is overwhelmingly formed. Abbreviated is indication of formation of certain complex species. The first one is beginning correspond to the region in which metal ions are uncompressed. In this region of low pH, concentration of unprotonic species of norvaline is maximum, and this species is non-compression. Figure 5 reveals that aluminum third, chromium third, and iron third ions form their first complex movement toward negative electrode. Hence, the norvaline anion species must have one norvaline species combined with trivalent aluminum, chromium, and iron to form the 1:1 cationic complex. Now, figure 5 is not given here. Maybe this will not have the figure 5. So, in the figure 5, the first plate will be the mobility of the free metal ions. Second plate will be the mobility of 1:1 cationic complex, and third plate will be the mobility of 1:1 metal complex. And all these are in the cationic region. Now the third plate in each case is still in the positive region of the mobility curve, showing the cationic nature of metal ligand complex. Hence, the two anionic species of norvaline have combined with trivalent aluminum, chromium, iron to give the 1:2 cationic complex. Chemical literature also assigns the prominent chelating properties of the unprotected anionic species of norvaline, ruling out any such property as deuterion. This is 21, not the 37. In view of above observation, the compression of metal ion with anions, ligand norvaline anions, can be represented by the equation 1 and 2. Where M is the trivalent aluminum, chromium, and iron, L minus is the norvaline ligand, 1:1 and 1:2 metal complexes, and their stability constants are K1 and K2. The metal spot on the paper is thus a combination of uncompressed metal ion, 1:1 and 1:2 metal complex. The spot moving under the influence of electric field, overall mobility is given by the equation of the 3, which is given by Joker, reference number 22. And this equation, on taking into consideration the different equilibria, this equation is changed into the useful form of this equation number 4. U is equal to E0, U1 K1 L minus U2 K1 K2 L square upon 1 plus K1 L K1 K2 L square, where U is the overall mobility, U0 and U0 is the mobility of U0, U1 and U2 are the mobilities of metal ions, 1:1 and 1:2 metal complexes. The potential constant of pure norvaline also measured by the same paper electrophotic. And these are values are found to be our first dissociation constant 2.31, second dissociation constant 9.65. We are determined by the same paper electrophotic, and these are the formulas, equations showing how they are dissociated. For first dissociation constant and the second dissociation. Now, using the potential constant of pure norvaline, concentration of norvaline anion is determined for the pH value of interest from which can be calculated. This is the concentration of norvaline anion is equal to total concentration of norvaline upon 1 plus H, pK1 plus pK1 and pK2 are the dissociation constant of norvaline. So this equation is used to calculate the concentration of norvaline species which combine to the metal ions, where L is the total concentration of ligand norvaline 0.001 mole per liter. pKa1 and pKa2 are the distance constant. Overall mobility will be equal to the arithmetic mean of mobility of uncompressed U0, that of first compressed U1 at pH, where K1 is equal to 1 pound concentration of ligating norvaline species. The second stability constant, K2 of the 1:2 complex, calculated by taking into consideration the region between second and third plateau of mobility. First stability constant taken into consideration of first and second plateau. Second stability constant taken into consideration of second and third plateau of mobility. And value of calculated values of K1 and K2 are given in table 1. These are the known literature values are available. Only calculated values are available for the aluminum third, chromium third, iron third with norvaline K1 and K2. First stability constant and the second stability constant. Now, discuss. It is clear from the table 1 that first and second stability constant of aluminum third, chromium third, and iron third, norvaline complexes follow the order. First stability constant is more than second stability constant. Log K1 is more than log K2. The corresponding second stability constant values are found to be lower for all complexes. It is therefore inferred that quantity tendency of ligand decreases with high state of aggregation. In other words, metal progressively descends tendency to linkage with a ligand or progressive filling of vacant orbital. This condition is universal validity as given in the literature by reference number 23, 24, and 25. The molecular structure of norvaline is given here. Norvaline structure is given. It is also clear from the table 1 that stability constant of metal norvaline complexes follow the order. Iron is more than chromium, more than aluminum. The high stability constant value of iron third norvaline complexes indicate a strong bonding between iron third norvaline complexes, may be due to greater affinity of iron cation with oxygen donor ligands. Now, the stability constant of metal complexes can be very easily calculated by this technique. Therefore, the present method has significant advantage over other methods, just like polarography, potentiometry, solidity. There are so many reported in chemical literature for the determination of stability constant. According to standard deviation statistics, the precision of method is limited to that of paper electro forces, and uncertainty in the result is plus minus 5%. Hence, it cannot immediately replace the most reliable method, even though new approach determine further development. The high stability constant value of iron third norvaline complexes indicate strong bonding between iron third cations and norvaline ion, whereas the low stability constant value of aluminum third norvaline complexes indicates weak bonding between aluminum third cation and norvaline ion. Higher stability of iron third complexes may be due to greater affinity for oxygen donor ligands. Now, this is one of the proposed structure for Ml2 plus bonding complex, where the two anionic species have combined with metal ions. Now, conclude. The following conclusion can be done from the present history. Number 1, aluminum third, chromium third, and iron third are significant for biological system. As such, they are toxic. Norvaline can be used to reduce the level of these metal ions in the biological system. Second, Ml2 plus complexes are found to have low stability constant values and less stable in comparison to binary complexes, Ml2 plus, than the Ml2 plus complexes. The third, stability constant of Ml third norvaline complexes follow the order iron greater than chromium than aluminum. Next point, iron third metal ions have shown greater affinity with oxygen ligand in comparison to the chromium third and aluminum third metal ions. The stability constant of metal complexes can be very easily calculated by the technique. So the present paper on technique has significant advantage over other methods reported in chemical literature for determination of stability constants. Future work, which has not been done right now, is to prepare aluminum third, chromium third, and iron third bonding complexes with norvaline at optimum condition mentioned in this paper. Characterize them and study their possible medical potential as therapeutic agents. References. These are the references. Number 1, Banerjee, Everyman Science, 1995, Mujika et al., Computational and Structural Biotechnology Journal, 2014. Number 3, Zhao et al., Mali Course 2022. Number 4, Migenser and Gibbons, Metalonics 2023. Livik et al., Annals Agriculture and Environmental Medicine 2014. 6, Karajiski, Frontiers of Immunology 2021. Number 7, Abdullah et al., Frontier Plant Science 2024. Number 8, Rolik et al., Biological Trace Element Research Springer 2024. Number 9, Lu et al., Signal Transaction and Targeted Therapy 2024. Number 10, Kulajenska et al., Biomedicines 2024. Number 11, Contour Girish, International Journal of Molecular Sciences 2023. Number 12, Anand, International Journal of Molecular Sciences 2024. Number 13, Achkari et al., Biomedicines and Pharmacotherapy 2024. Number 14, Jimenez Perez et al., Molecules 2024. Number 15, Chin et al., Cell Death and Disease 2024. Number 16, Alvarez, Carino et al., Origins Life, Evolution Biosphere 2013. Number 17, Y. Kisho, Zone Electroforces, New Attempt of Onyx, Nankado, Japan 1972. Number 18, McDonald Ionography, Electroforces in Stabilized Media, Yearbook Publication, Chicago 1975. Number 19, Kolthoff and Belcher, Volumetric Analysis 1957. Number 20, Bogle, Textbook of Bogle, Quantitative Inorganic Analysis 1978. Number 21, Blackburn and Jones, J. Inorganic Nuclear Chem 1970. Now, Jokal, J. Chromatography 1964. Pathak and Joshi, Journal of Indian Chemical Society 1980. Number 24, Joshi, Indian Journal of Chemistry 1982. Bhattacharya, Journal of Scientific Industrial Research 1981. That's all for my presentation. Thank you all for your kind attention. Special thanks to moderator and organizer of 5th edition of Chemistry World, Professor Alexander Bradley. Thank you all again. Thank you all.